We have 4 talks in this session. The first talk is a journal paper track talk given by Stefan Edelkamp on planning with continuous numeric action targets.
Hello everybody, welcome to the show. I'm Stefan Edelkamp and this is joint work mainly done by Florian Franke. It's his PhD work which I'm trying to supervise, and this has been published not in JER or AIJ but in Mechatronics, so maybe you are not aware of this work. So the time is too long to repeat. We have a new planning system that I will present to you, so that's good. It does do many different things, and we will look at combining planning, interval analysis, and non-linear mathematical optimization. So this already is something. So we are not doing optimal at all. So to get you into this continuous numeric action parameters, or how Maria likes to call them, control parameters, we will go to PDD-based planning with numerical fluence and the challenges that come out of it, applications to multi-agent shop floor control, where we start out to get industrial applications, and our two-tier planning system results conclusion, as always. Okay, this is the best picture you should remember. Here you have numerical planning. On the left side you have the state I, on the right side you have the state I+1. In the middle you have an action, and it has some precondition that x plus y is smaller than equal to 8, and y also has to be something, and it's about pouring. This picture says, oh, well, we have that many liquids to the left and that many liquids to the right, and this is what we all can do with at least some of our planners that can deal with numbers. But what we can't do is the following, neither in PDDL, any of these PDDL things that are around, is to have a parameter z, which is in between 0 and 1, and that says not pour everything but pour a bit. We do not know in advance how much the bit is. Okay, so this will then have, I hope you can see these numbers. This will have some effects on the next states, which we usually cannot exactly know, but only in some intervals. And x is between 2 and 6, and y is in between 0 and 4, according to these effects. And one question could be, is the condition that x is bigger than 4 and y is bigger than 3, is it actually satisfiable? According to the interval it is, but if you look more closely to the problem, it actually isn't, because the overall amount does not change. It has been 6 in the beginning and also 6 in the end. So actually we have some problem that our interval arithmetic maybe is not precise enough. So this is the setting we are concerned with. We have drilling or milling machines that are in a shop floor scenario. There we have orders that come in dynamically, and we have a planning system that runs in steps, and it recommends either to produce or to maintain some machine if they are broken, and sometimes to repair them, or to be idle. That's the I. And orders are accepted. Some are then produced and sold. Some are actually, after accepted, they are cancelled because maybe a machine broke or so. This is always the case in optimization and controller optimization, that there are conflicting goals. We want to have a large number of assigned jobs, or at least a good utilization of our machines, which were expensive. The throughput should be high. And so there are conflicting goals that you can see here. One I want to minimize, one I want to maximize, and this is no longer simple. And if you have those real valued parameters, in this case the speed of the machine, the drilling machine, it removes metal from some precision gears or some engine part, then you actually have that the real duration is this line, and the modeling in key performance indicator is this, and the optimum is somewhere here. And it's not only like the duration which counts, the quality of the workpiece is also depending on the speed how you produce it. It's not only quality, what you have is production costs, is also depending on the speed of production. Machine wear out is also something we should be aware of, that the machine may break, and you have to optimize all of them in one go. They are somehow dependent. So this is planning with key performance indicators. But what we look at here is a speed parameter, which is actually a numeric parameter. If you make it fast, like speed 1, then the wear out is too big, it's 1, and the quality is low. If you make it very small, then the wear out will be just 10% and quality is big. But there are lots of other opportunities in between. Actually, there are an infinite number of them. And you could either produce precision gears or engine parts, and then you think about, well, how can I do this with PDDL? And we extended PDDL not so big, but just by introducing a requirement flag, which calls numerical parameters. Then this parameter does appear in the parameter list, and then we have that duration may be dependent on the speed. So the duration here, and the speed parameter is here, and the speed parameter appears here and there. We have this normal PDDL representation of at start, at end, and here also we have members like orders that come in and out. But here the speed parameter will be changing everything in this function. And it's a number. Okay, and sometimes you do plan and you have a maintenance level of 0.5, and if you produce too quickly, then the machine already fails easily. So if you generate plans, then this one would fail, this one actually is okay. The other one is also not working fine because the maintenance level is falling below 0.1, below 0. Okay, so these are plans that can be produced, and these are generated by a combinatorial planner. Could be your planner. We just have some enumeration method, no FF, no fast downward or anything. So we just enumerate them and have some constraints that take care of some infeasible plans, and then we get some that are already out and some that are going to the next stage. So we have utility to sort them. By the right hand point of this interval, we have utility and we pass the n-best plan to the numerical optimizer. So a plan is partially instantiated. So the speed parameter is in this plan is not yet fixed. So we use a wonderful numerical optimizer. It's called differential evolution. It can optimize everything, but it's pretty slow. This guy then finds out, oh, this plan is not possible. So there is no instantiation to the speed parameter that makes this plan feasible. But some are, and then we have a planning and execution loop. We just add, after each step, we give the plan back to the shop floor, and then it's actually executed. Okay. And then we progress, and sometimes even that fails, so that execution fails because there are real-time constraints that are not modeled in the PDDL. Then we have to actually repair the plan and update. Okay, here we then see some results. So about this dynamic multi-agent shop floor scenario, we have 2 mills that you have already seen, 2 order templates and lots of orders coming in. And well, we have changed the number of plans that go from the combinatorial planner to the next stage. And in the next stage, our constraint reduces 819 billion to some 17,000 plans, and then we give the best, say 93 to the planner. And 93 is a number that actually worked, where we do not have any plan repairs and not any cancelled orders that we could not produce. So we checked with incrementally increasing n, and then you can see that there is some repairs depending on the limit of the plan see that also has consequence on the money for the producer, like the company owner, and here this monetary balance is best, and the time to run is also best. So this is a plan that you probably want to execute then on the shop floor. Okay. We are already done. So planning with continuous action parameters is a nice addition to the PDL setting that we have. So PDL 4 will have it, maybe, or 5. And we have that our planner is quite complex. It can do nonlinear equations, and it has some constraint satisfaction issues that you can put on top of it. To some extent it's domain dependent, to some extent it's domain independent. So the approach is domain independent, but we are looking at shop floor scenario because we really want to do logistics settings that appear in practice. And there are some papers besides this journal paper that look closer to it on the PDL side, on the planning side, and also on the key performance measurement side, which at least the guys in business, they think about key performance indicator that they want to reach in this. Our two-tier planning system is great. It has interval arithmetics inside. It uses a mathematical optimizer, satisfying and dynamic plan repair. And as far as now, we have results that look promising. Outlook would be to have more insights to the rules, for giving the plans, maybe using the planner that is already there, to use heuristics in there, and more advanced constraint satisfaction problems. So thank you very much.
Any questions? Yes.
Thanks. Very interesting. So there's something that might confuse me a bit. So you said it's discrete time, but I saw you have derivative actions with infinity, but you're changing durations. So do you just discretize time?
Yeah, it's stepwise to some extent. When I have a plan, I give it to the executor and it will come. And so it is discrete time, but you're right that the speed parameter somehow makes also duration of some actions not discrete, but there is a discretization thing that can be optimized. But we want to have a loop that plan and execute, so we have discretization, at least for execution.
Insights have you got into the kind of domain independent heuristics that might be possible?
For us it was more that lots of, so implementing the entire piece was so hard that we could not even concentrate on planning, so that is the thing that comes up next, and you also already have a student that does it. So I will just take them this planner and then it's fine. And so insight is that this constraint satisfaction that you have to look at, like this interval arithmetics, and so it's not only planning, so you have to look more closer to these things.
Maybe it's time to standardize PDL with control parameters because there's three versions.
You're on it.
Right?
With this help.
Time for one more question. So here you see on these slides that it's really not possible to solve with traditional optimization or constraint satisfaction method, or that you would struggle. Did you try? I don't know, MINLP solvers or?
Well, the thing is that this is at least nonlinear and so on, so we have not really dig too much into the numerical optimizer. This one did work by magic. This differential evolution is a genetic something that can optimize everything. And of course, if you want to perform better, you have to look more closer to better solution. I think you will have to restrict the kind of problems you look at, like linear constraints and those things. Then you may get faster optimization.
Thank you very much. another of our esteemed Michelle Lane and Michelle Woodman. Our goals is going to talk about state utilization in temporal and numeric. Okay, well, so we've made it to Friday. We made it onto the stage for my talk. This is great news. So, what we're looking at here is memorization in temporal planning. So, the first thing I'm going to tell you is what's memorization and why is it important. So, we are doing forward search to do planning. And if you just think of a standard script planner, we've got a good little driver log example here, everybody's favourite domain. So you start from your initial state, right? These are the position of the driver, the truck, the package. So there are AAA. And we can apply our actions, load and board, and we get to these two new states. And we keep expanding here. I'm just doing breadth first search. Already I've hit the same state again, right? Because I can load, and then I can unload. You might think, well, the planner's just being stupid, right? Because it's inverting its own action. I will make two arguments here. One, planners are stupid. And two, that's not the only way you get to the same state again. So here, if we carry on expanding, we've done load board or board load, so this is another way of getting to the same state, right? To find permutation symmetry. Again, we've got to AA again on the right there. We keep going, get to the same place again, and so on and so forth. So you can see from how coloured this graph is, that actually I've coloured the same state, the same colour each time, actually get to the same state a lot. Effectively, we are searching a graph as a tree. So we need to do something about this, otherwise we're duplicating the same search space all over the place and things become infinite. Just one more way of getting to the same state, you see this TCT, TCT. This will become important later, because if you drive from, I'll go back up. So if you drive from A to C via B, that is the same state as driving from A to D via C if you're doing strict planning. There's an optimality issue there, but it looks nominally like the same state. So in a strict plan, memorization is pretty simple, right? So you remember all the states visited, they are sets of facts. If you see one that has been generated before, so every time you generate a state, you look at it, say, have I seen it before, you throw it away. There are a lot of complex issues in memory management and so on, how to efficiently represent a state. That's not what we're talking about here. But in general, it's a much simpler problem. Numeric planning is slightly harder. This is stuff from Metric FF back in 2000. You can basically, if all your preconditions are some variable value is greater than or equal to some value, then simply you can work out before you start planning, this is always better for this value to be bigger, and so you can prune any states that Pareto dominate another state that you've seen. And if you can't do that, then you have to keep the same. So we are in a temporal planning setting instead. So this is pop-up in one slide, or the relevant part of pop-up in one slide. So to do temporal planning, instead of applying single actions like in strict planning, we apply start and end snap actions. So we split each action into two separate actions. And every new action is added to the plan after the actions to achieve its preconditions and any actions that condition on its delete effect. So this avoids any conflict with, we don't delete something before. So the key thing here is that every new action is added after all other actions in the plan, ordered after some action in the plan. It's never ordered before some existing action in the plan. And this is true for your decision epoch planners as well. They just order every action after the last action in the plan. Once we've done our planning, we've applied our action, we use a simple temporal network to check that the temporal constraints are valid at each state. The temporal constraints are valid, we can keep it. If they're not, then we're going to prune the state. So, let's have a look at time then. So we're now in this driver log domain. This is a temporal problem where we've got to get to E in time. We've added this action
work now. So this has duration 7, so this adds the fact that the driver is at work. So he can only do things whilst he's in work, and we want to get to E, we want to get our package to E. So here's a possible plan going from A, B, C, E. Let's say we consider this first. Now, obviously this plan is not going to work. Okay, because this level of activity does not fit within this 7 time unit work action. So the actual plan, what we need to do is drive A, D, C, E. That's the only way to reach the goal. However, in this plan, you can see where it's red here. This is where we make a mistake, right? We make the mistake there. We've decided to drive from A to B. This problem is now no longer solvable. But if we carry on going, at this point is where we realize drive C to E. Only at that point do we realize our plan is temporally invalid, right? So if we were to try and end work there, we would realize that's the first point that we can't actually fit all this within this envelope. However, this state here, at the end of drive BC, this one in orange, will be memoized, right? We have expanded it, we have visited it. If we just do strict memoization, this state where the driver and the package are in the truck at C, we would memorize it if we just did strict memoization. And now that would prevent us from ever visiting the other path, A, D, C, E, right? So, in the presence of open actions, we actually strict memoization is incomplete. In the general case, supposing we hadn't introduced this work action, we just had the plain drive along, and we still went round that way via B, then we're not incomplete, but we've lost optimality, right? Because we're going to prove the optimal plan if we go via B first. So, okay, so this is just an illustration. So we go down this branch of the search space first, we get to C, then this branch of the search space is never going to be expanded. So the first thing we did is say, well, when can we use strict memoization in temporal planning? And what we found out is that although it is not optimal, we lose optimality in the absence of open actions, it is still complete. And this is just a brief sketch of the proof. So incompleteness arises in temporal planning if we've got some state which we've reached by a plan, and we've memorized that, but that later inevitably leads to a temporal contradiction. There's no valid temporal extension of that plan. However, there is some other plan to reach that state which would have a valid temporal extension, but we consider that after this one, after we've memorized it. So for a plan to be temporally invalid, the STN, simple temporal network, representing the plan, must contain a cycle. Okay. So this is the plan to the state we're considering so far. T. This is it's a simple temporal network representing the plan. This is a simple temporal network representing some hypothetical valid extension of that plan. So for there to be a cycle in this whole network that joins T and T prime, so an extension of the plan to this state, then there must either be a cycle in T, which means that's an invalid plan to reach this state, and in that case we say, okay, if there's a cycle in your temporal network, you prove that state and you don't memorize it. Okay, so you never memorize a temporally proved state. So that gets rid of that case. On this hand, if there's a cycle in T prime, then that is not a valid extension of any plan, right? Because it's a temporally invalid plan. So the only case where there can be a cycle in this complete plan is where there's a cycle between T and T prime. Now remember at the start of the talk I emphasized that all actions are ordered after existing actions in the plan. So not after every action, but there is never the case that you will add an action ordered, explicitly ordered, before some action that's already in the plan. So that is a backwards edge from T prime to T. That's an after ordering constraint. The only time you can ever get a forward edge in a temporal network is a duration constraint, so a maximum duration constraint added to the plan. So for a cycle to occur between these two networks, there must be some action which starts here and ends here, which means that there was an open action in the state we're in. It had started there, but it hadn't yet finished. So if we have no open actions, we are complete. So we propose two new techniques for data memorization in temporal planning. Well, the very obvious thing you can do is use strict memorization in steps with open actions, otherwise keep all states, right? That's an obvious benchmark. That is not optimal, but it is complete. And our two novel approaches were isomorphic partial order pruning and fact availability. So let's start with isomorphic partial order pruning. So these are three plans, as suppose they're generated by Hopper. These things in here, these lettered boxes, are snap actions that have been applied. Hopper would consider all three of these to be different plans, because the step IDs of the actions are different. And in the general case, if I apply actions in a different order, I will get different ordering constraints in my plan. I have to keep all those different plans. However, in this case, because there are no ordering constraints between B and C, each one of these plans is actually equivalent. And what we wanted to do is work out, okay, well, how can we keep the states we need to, but get rid of these genuinely isomorphic partial orders? And the first thing we tried was very naive. Okay, we'll just run graph isomorphism on the plans of each state. This doesn't work. But instead, we came up with a technique where it's not actually a general isomorphism problem. We can exploit the structure of how these things are built. So what we effectively do is we impose an arbitrary ordering on the actions by action ID. And then what you can do is you can take a partial order plan that you've generated as you go along, and you can compute a canonical plan. So that is, you basically do a topological order traversal, and you break the ties by action ID. So here, you get A, F, and then B, C, G. So in this case, my topological ordering is alphabetical, right? So A and F, because they're ordered, and then B and C, the tie is broken by ID, and then finally, we get G. So instead of just memorizing any state, we memorize the canonical version of the plan, and then every time you generate a new plan, you quickly compute its canonical form, and if that canonical plan is already memorized, then you can prune the state. And this is great because it remains sound and complete, so we're not losing anything, we are only pruning literally identical graphs. Second approach, fact availability times. Now this one has a few more restrictions. So, as you know, with our planners, we like to handle absolutely everything. We don't like to trim anything out. But this does allow you to do a bit more pruning under certain assumptions. So the real actual crux of the assumption of this is it's always better to do things earlier. So this list here is at times when it might be better to delay things. So if you've got continuous or duration-dependent effects, you may need to delay your actions to make your numeric constraints work. You've got time-dimensional literals, you may need to be able to do things later. And also, I've never seen this, but you could write the metric and maximize makespan. If you want to do that, don't use this pruning, right? So the idea here is it's better to do some things earlier. So, first of all, you can solve a simple temporal network for a given plan to find the minimum timestamps for each action. So that's the earliest time at which you could apply each action. And this is similar to numeric planning then. You compute the timestamp, so the last step that added P, the last step that had a precondition on P, and it's the same for all the numeric variables. And then basically if you can use P and change P early other for all variables, then you can prove based on Pareto dominance. So we did this, but then we had a problem. It wasn't that great because when you are going in two different directions, you still get some problems. So these two plans again, ABC, ADC, you see here there's a difference between them, right? We can change the fact that we were at B at time 3 here, and we can change the fact that we were at D at time 2 there. But that's actually not interesting because we're actually no longer at B or D, and in order to get back to B or D, then actually we're going to have to change from being at C, right? Those facts are mutex. So the idea here is to use a mutex group, and then you basically change your change P and use P function to be the maximum of the time you can change the last thing that was true in the mutex group. That gives you a bit more time. So this is just a summary of our approaches and when not they are optimal or complete. Notice we have a strict dominance, this is a theoretical dominance, on the order of the pruning power of each one. So strips proves provably more than fact availability time, which proves provably more than isomorphism, which obviously proves more than keeping full states. So basically you can combine these together in arbitrary ways. So you can use one memoization technique when there are open actions and one memoization technique when there are no open actions. You do this on a state-by-state basis. So here are some results. So we evaluated on all the temporal IPC domains. We were using the TFD translator to generate mutex groups, so we could only use those domains supported by the TFD translator, which is most of them. And we're using an implementation of pop-up. We're just doing WA star with W equals 5 just to concentrate on the memoization aspect. So as you can see, memoization is quite important. This is keeping all states versus doing fact time plus isomorphism pruning. So the first one is where there are no open actions, the second one is where there are open actions. So this is completeness and optimality preserving, but as you can see, we're getting a lot more power than we would had we kept all states. And in the second case, we've got just completeness preserving, and as you can see, we're still doing a lot better. So one interesting result was that stretch pruning actually, although it is not optimality preserving, because basically you're just much more zealously pruning, you actually can find solutions much more quickly. So in domains where you happen not to be pruning optimal solutions, you can actually get better solutions just by virtue of being able to find solutions more quickly. I'll just give you the headline summary of the results then. So if you have, let's see, overall, so fact availability times plus isomorphism pruning, we preserve completeness and optimality, and we're solving 100 more problems in total than keeping all actions, and we actually beat doing strict pruning overall because of the problems lost to incompleteness. And fact availability time and isomorphism pruning is actually completeness and optimality preserving, and it solves 100 more problems than keeping all the states, and only 14 fewer than the best suboptimal approach, so we don't pay too much for maintaining optimality. Final comment, isomorphism pruning plus isomorphism pruning is safe for any setting. So it can be used if you've got continuous effects, if you've got time initial literals, anything like that, and it's much better than keeping all states, which is previously what we basically had to do. So I'll finish there because I'm short, and thank you for listening.
A nice talk. I was just thinking about the isomorphism pruning. Obviously this is important in a temporal setting and these results are beautiful. But have you thought of other settings where a similar isomorphism pruning technique might be useful? Where you've got constraints other than temporal constraints, or indeed...
Where you've got what's that?
doing memorization in a different setting in planning where there may be other kinds of constraints? I mean, it strikes me that isomorphism pruning might be able to be utilised in a different way for different kinds of problems.
So we do have kind of very expressive planning problems, right? And basically we put the expressive parts of the problem into a linear program or an integer program. So actually what we're doing at state level is kind of propositional, and the validation of all the numeric stuff is done in the MIP. So certainly, I mean, it can be used in all the settings. You've got continuous numeric effects, you've got duration-dependent effects. It doesn't matter, right? Because it is the same state in the search space. And one of the things that's actually really great about the search in Pop-up is you consider so many different plans within one single state, because you've got this MIP doing that reasoning. And we weren't really getting the full benefit of that originally, because all these states were coming up again and again anyway, we were considering them again. So I think now this has really helped in terms of the performance of the planet in very expressive settings as well.
More questions? So I was wondering, so do you have any guarantee that some of the kind of pruning that you do is the strongest you can do to preserve some property like or optimality? Is this even envisionable that we prove that?
We haven't done anything. We just basically we said we wanted something that was optimal and was complete. But no, we don't have any guarantees that there is not a better way to do it. I would imagine that there are some more things that you can do on top of isomorphism pruning to improve it further. But at the moment, that's the best we have in terms of optimality and optimal and complete strategies.
Questions? Okay, thank you very much. So next talk will be given by Sambaran Banjukanai. Can we describe? Yes. And this will be the planning for curtailment of renewable generation.
So good morning everyone. I am Sambaran Banjukanai from ICAPS Research in India. So I am presenting our paper on planning curtailment of renewable generation in power grids. Before going to the technical details, I just want to give a high-level summary of smart grid and renewable generation. So smart grid is basically the advanced version of conventional power grids. So it's a combination of information technology and process automation technology with our existing electrical networks. So renewable generations such as wind power generation, solar power generations are the key components of smart grid. Typically these generations are distributed in nature, which means that there are multiple and small-scale prosumers generating power and feeding in the excess energy back to the electric grid with the incentives given by the utility companies. To ensure stability of the grid and to ensure defined network constraints, utility company at any given point of time has some maximum intake energy capacity from all the prosumers. So basically at times of renewable supply excess, the grid operator selectively refuses to buy power generated by a chosen set of prosumers, which is referred to as the curtailment. Now there are two basic goals of curtailment. As the utility has its own required energy limit, so the total energy collected from all the prosumers should be close to this intake energy limit. And also curtailing a prosumer is basically you are not taking energy from that prosumer. So which will basically incur some loss to that prosumer. So this loss should be fair or equal to all the prosumers over time. There are also few challenges of curtailment. First one is that the energy produced by individual prosumers are not known quantity ahead of time. And there are also defined localized effects. For example, dust accumulation on solar panel. So these are like localized effect of inefficiencies, which is difficult to predict by all the standard energy predictors. And it is also difficult to estimate the fraction of energy used by the prosumers and thus net feeding to the grid. Also scalability is another issue because there can be millions of prosumers under the utility and the planning granularity can be as small as 5 minutes. So the approach should be able to handle this tremendous amount of data. So this is the mathematical notation that we have used. So N is basically the set of prosumers. We have divided total time into capital T time slots, and the estimated generation by each prosumer is denoted by the vector Gi, which consists of Gi1 to Gi where Gi is the estimated generation by prosumer I at time step t. The intake energy limit of the utility is again denoted by vector T, which is from T1 to Dt. Again, Dt is the energy intake limit by the utility at time t. Now, as I mentioned that there is some uncertainty in the power generation, so the net generation can differ from G's, that is the expected generation. So this uncertainty is modeled by this fraction MIT, so that your net generation is MIT GIT. So MIT is basically typically a number from a fraction from 0 to 1. And the exact value of MIT can be known at time t only if the prosumer I has not been curtailed at time t. And our goal is basically to understand which prosumer to curtail at what time. So to model that, we introduce these variables xi t, where xi is 0 if and only if the prosumer I is curtailed at time step t. And we have this utility given constant which says that total energy collected from all the prosumers at any time step t should not exceed the energy intake capacity dt given by the utility. We also want to ensure fairness into the system. So for that we have introduced this metric FIS, which is a fairness metric for prosumer I until time s. So if you look into this expression on the right hand side, the first component is basically the ratio of the total energy collected from all the prosumers till time s minus 1 to the net generation by all the prosumers till time s minus 1. And the second component is basically the total collected energy from prosumer I till time s minus 1 to the total net generation by prosumer I till time s minus 1. So here the FIS can even be negative, and this is the value of FIS. More is the fairness for prosumer I. Now our objective is basically to maximize the total feed-in energy, and also we have to maximize total fairness. This number gamma it basically weights these two components. Now if you look into this objective function carefully, you can see that estimating the values of MIT are required to solve the problem efficiently, which is called exploration. But for that we have to select all the prosumers sufficient number of times, which can lead to a poor value of the cost function. So another approach can be to select the prosumers which already have good estimated values of MIT. This we call exploitation. But this can also lead to a poor solution because we may miss out some good prosumers as they are still unexplored. So this idea matches to the classical problem of exploration-exploitation dilemma. So a well-known instance of this exploration-exploitation dilemma is multi-arm bandit mechanism or MAB. So typically there are M arms or like this kind of gambling machines with arm I having an unknown reward distribution with unknown mean EY. Now at each round the player selects one arm to play and observe the reward, and the ultimate goal is basically to maximize your total reward over time. But the problem is that we cannot map our problem directly to MAB, because in our problem at each time step we select a subset of prosumers instead of selecting a particular prosumer. So we are using another version of MAP which is called combinatorial multi-arm bandit or CMAP, which got introduced in 2013 ICAPS paper. So here a super-arm case is basically a subset of arms, and at each time step the algorithm selects one super-arm to play and outcomes of all the played base arms are observed. Again the reward is basically it's a function of all the outcomes of the played arm. In the simplest form it is just the linear sum of the observed outcomes, and it can even be some nonlinear function of these outcomes. Again, you want to maximize your reward over time. Now, according to that paper, this reward function should satisfy two properties: monotonicity and bounded smoothness. And also, if you look into this objective function here, so it's basically maximizing RUS over all supersets. Now, the number of supersets are basically exponential in nature. So instead of getting the exact solution, you want to have this alpha beta approximation parallel. So the good thing is that in that paper they have proposed this CFCP algorithm, that is combinatorial upper confidence bound algorithm, for which they have shown that the regret is upper bounded. Now this is the formal mapping of our problem UPDC map. So here basically each prosumer is mapped to one arm, playing which corresponds to not gardening that prosumer in that particular time step. And this is the reward function for a super arm S. It is basically a subset of prosumers. Now if the total estimated generation for that subset of prosumers exceeds dt, then there is a chance that the total collected energy might exceed that dt, which is the energy intake capacity given by the utility. So in that case the reward is minus m, where m is a very large number, potentially infinite, and otherwise it is just the objective function, it's just the cost function of our optimization formulation. So if you again look into this reward function carefully, you can see that it matches to the classical knapsack problem. So here basically each prosumer is an item. The weight for each prosumer is GIT, and their value is this function. And the size of the knapsack is given by dt. So as knapsack is NP hard, we want to use this polynomial time approximation algorithm for knapsack, which guarantees these approximation factors of alpha, where alpha is typically a number from 0 to 1. And we have also shown that the reward function satisfies both motonicity and bounded smoothness properties. For the sake of time, I will skip the details of this algorithm. This is just a CUCD algorithm for this tidal wind problem. So this is the dataset that we have used. This is a solar generation, solar dataset from different for 20 prosumers in Melbourne in the month of November. So we have collected data from 7:30 am to 5:30 pm, and the cardinal planning is to decide the subset of prosumers to cardinal in intervals of 5 minutes. So we have proposed two extensions in this case. The first one is time of day based context. Here we have divided this 10 hours into 5 contexts. Each context is of 2 hours, and we have plotted the average mean for a selected prosumer. As you can see that these mean values differ significantly for each context. That's why instead of learning one mean for each prosumer, we try to learn one mean per context per prosumer. Second extension is basically daily adjustment. Here this is the plot of the average generation of all the prosumers over different days. So you can see that there are some days where this average generation is significantly less than the average. So what we do, for these days we have another set of variables which actually check the total generation so far and adjust the mean appropriately. So we got total 4 algorithms: CUCD for cardinal, CUCD with time of day based context, CUCD with daily adjustment, CUCD with both the extensions. And we have 2 algorithms to compare. First one is rand ones. It's a naive algorithm. It just randomly permutates the prosumers and sequentially selects as many prosumers as possible, satisfying the utility given constraint. Second one is optimal clairvoyant algorithm. As you can guess from the name, that this algorithm assumes to know all information in future. So this is not possible to implement in practice, but this is just to compare the performance of our algorithms with the optimal one. Now, before we show all the results, we have to decide the value of gamma in the objective function. So in this plot, you can see that as we increase the value of gamma, the total energy collected, which is on the left hand side, it reduces, and the fairness, which is on the right hand side, it increases. So we choose the value of gamma to be 10 to the power 6, for which both the components have reasonable decent performance. So this is the energy collected by different algorithms over time. The pink line is basically the target collection of the utility given energy intake limit over time. As you can see that CUCD daily in this figure and context CUCD daily, they are actually performing very good, and they are very close to the target collection, which means that daily adjustment extension has better impact on the algorithms. This plot is on the left hand side shows the ratio of the performance of these algorithms with the optimal one. So as you can expect that rand is performing really bad over time, and CUCD and context CUCD are somewhere in between, where CUCD daily and context CUCD daily, they are performing really good. They are almost equals to 1, and you can also see the learning rates over time. Second plot shows the runtime of CUCD over number of prosumers. So as you can see that after or from 60 is kind of linear. So this is because of the using the knapsack approximation algorithm. So if you have used the exact knapsack solution, you can see it to be exponential in nature. So that's all I have. So thank you very much for your kind attention. So I would like to take some questions now.
Question. So in practice, and this is going to be relevant once you've got lots of prosumers, thousands, tens of thousands, you're going to have to start taking into account the network, because it's not just enough to have a constraint globally that you want to have the total generation less than some total bound, but really you will have to take into account constraints on capacities of individual nodes of the network and voltage and things like this. Is there a chance that you might be able to extend this already?
Yes, that's a very good question actually. So though we have presented the work in the utility or on the aggregate level, but the same work can be implemented even on the feeder level or maybe on the DT level if possible. Because I think the technical details would remain same, but your energy intake capacity that will actually change depending on the number of prosumers or the network constraints and all.
So I guess you have to first decide at each node, looking at the network at each node what you can allow, and then selecting the prosumers.
Exactly.
Yeah.
So multi-banded algorithms converge, right? Because they're designed to converge to optimal, whatever. And so you have some extensions, dealing with the variance on a day-to-day basis, right? And from hour to hour. But what if there's suddenly like a massive shift of power use, like I don't know, summer versus winter or something like that?
Right.
And then you've converged to something that's suited for the other regime.
Yes, I mean, so for that's actually our second extension is daily adjustment that will actually try to capture all these scenarios. So as you can see that on the 6th day the generation is really low. So what happens is at the starting of the day you see the generation is low. That's why you adjust your main appropriately for that day. But if there is like very sudden change, then I think it will be difficult for the algorithms to capture that.
So we've run out of time for questions.
Okay, thank you.
Going to talk about another application of planning to energy systems. That's going to be about unique commitment.
Hello. Today I'm going to present a joint work with Daniele Magazzini in collaboration with the STEM in Durham University, and in particular we are looking at the unit commitment problem. This is a power system problem that is the problem of finding which generator unit to switch on and off in order to satisfy a demand at the minimum cost. So in this talk I'll first introduce in more detail what is this problem and why it is challenging, and then I'll talk about the planning approach that we adopted. In particular, I will talk about the PDTL plus model that we have developed, but it turned out that the planner that we had available weren't very scalable, so we had to use a decomposition to model the problem subparts, and we had also to exploit some symmetry of the problem in order to boost the performance of the model. And okay, just finally give some future directions for this work. So, as I said before, the unit commitment is a power system problem where we have a demand that we have to satisfy. And we focus on a fixed horizon of time of typically 24 hours. And we are considering thermal units. We need to find when to switch on and off these power units, and we want to know the output, the power that each unit output in order to minimize the total cost. Each unit has different constraints. Typically, we are considering this set of constraints. So the first one is that once a unit is on, it has a minimum stable generation level that it has to satisfy. And at the same time, we also can't exceed too much power, can't produce power that exceeds the capacity of the unit. Then we have also some temporal constraints. So for example, when a unit is switched on, we must wait a certain period of time before to switch it off again, and this is because the unit has to reach a stable condition. And at the same way, when a unit is off, again, we need a period of time to let the unit cool down so that we can then switch it on again. We have also a constraint on how fast we increase or decrease the power of a unit, and this is called run constraint. The objective function that we are considering is the production cost. So basically, we have a startup cost and then a cost for producing the power. And we can approximate this cost as a polynomial function of the power. And a good approximation is a quadratic function. The unit commitment problem received attention, it's always been studied in the power system community, but it has recently gained more attention because the power system are transitioning into a different system. So first of all, we have assisted to the market liberalization, so we should take into consideration some other constraints, for example, manipulation constraints. And then we are assisting an increase of penetration of stochastic resources, such as wind and solar farms. And the more these resources are becoming important, the more the focus is shifting from minimizing the total cost towards a more reliable power systems. So another change that we expect more long term is the introduction of storage devices that bring nonlinear constraints. And these basically are the challenges that we are sort of starting to face. So the power system, the unit commitment problem is popularly solved with mixed integer programming, and the model, however, are quite expensive because basically we need to discretize the timeline, and for each unit we need for each time point that we are considering, we need at least one variable to model the unit. And also we have a fixed discretization for the timeline. Instead, in planning, we have a model based on actions, so the model is should be more compact, and in principle we can have we can end the time in a continuous way. So this will bring a final level of optimization. Okay, so now let's talk more in detail of the DDL model. And so with this model, we need to basically capture all the constraints that I mentioned before. The first constraint is, of course, that we need to satisfy the demand. And for this, we have a derivative action that has a duration equal to the azimuth time that we are considering. And this action is enforced to start at the beginning of the planner, and it has to be observed to the end. Then we have a switch action. So this is another derivative action, and the duration, we can impose a duration constraint that is basically the duration must be greater than the minimum time at which the unit should be on. And this action model also the fact that when we switch on the power unit, we are already producing the minimum stable level of power. Then the ramp action models the ramp constraint. So basically, this action increases the power, increases the power of the unit, and the rate of change of this increase should be less. I mean, its pixel is less than the ramp-up limit. Then we have a process that runs when basically the power unit is on, and this process calculates the total cost of producing power. And in this case, we consider linear cost. And this is just an example of what a plan looks like. And you can see, for example, here we are switching on a generator. So we have power that then we increase here until we switch off the generator. So we use this PDL model with the planner Murphy, which is a planner that uses the validation, discretized and validated approach. For this, we tested the model first with two units and time horizons of 10 hours. And this is the problem is that the Murphy is not a metric sensitive planner. So if we want to minimize the total cost, we need to do an iterative approach in which we first impose a total cost limit, and then we find a solution, and we use the cost of that solution to decrease the limit of the cost. And this is an example of the solutions that we define for this problem. And basically, we terminate the problem, the process, when we find a solution that is not valid anymore. The problem is that basically with this approach we can't solve more problem with more than 2 units and 10 hours for 10 hours. And this is basically because we don't have a heuristic. And the second problem is because the planner spends a lot of time in searching what is the power level for each unit, the exact power level for each unit. While once the units are on or off, this is a relatively simple optimization problem that can handle in our way. So what we did is to decompose this problem into parts, because as I said before, there is a combinatorial part of the problem that is basically to find which units are on and off and when, and we use UP mapping to take care of this part, which also consider the temporal constraints that we have. And once we have the configuration of all the units, we can use an LPO linear programming model to find which the level of power for each unit. So basically, what we do is we use the search engine to find the configuration. Then we can call the LP or the model to calculate, first of all, to check if all the constraints are satisfied, and then to obtain a cost and an heuristic value for the state that we are evaluating. So for the evaluation function, we use a weighted evaluation function that takes the cost and the heuristic value, where the cost is obtained with this quadratic programming model. And basically what we do to obtain the heuristic function is to relax some of these constraints, and so no, we don't have the ramp constraint anymore, and we assume that all the units can generate from 0 to the maximum level without any temporal constraints. Okay, so then we also apply additional custom space search. Basically, we limit the number of actions, switch action for each unit, and we involve the video generation on. And these are valid constraint limitation that's they are not limitation. These are assumptions that are realistic when we are considering this problem. And this is an example of the solution that we obtain, the solution quality that we obtain for a problem with 8 units when we use a different weight in the evaluation function. And basically, we can see that if the weight on the cost is bigger, we are optimizing a bit more and we obtain a better quality solution, but obviously at the cost of having to spend too much time in finding this solution. And with this method, we can solve problems from 8 up to 122 units for a 24-hour hours. The other thing that we did is to exploit some symmetry. So basically, we we group together all the units that are that have the same characteristics, and so that the actions are not applied to the units, to the single units, but they are applied to this group of units. So instead of saying we want to switch on this particular unit, we say we switch on one unit of this group. And with this taking into consideration also this symmetry, we can solve problems with up to 400 units. And in this plot, I show the difference between the solution that we obtain and the solution with obtained with mixed integer programming. And we can see that we are still not close. We are not still beating mixed integer programming, but we are more or less 3% worse than that. But on this plot, here I show the difference in quality of the solution that we obtain at the first iteration of the planning, and the solution obtained with MIP at the same time at which the planning solution was found. And we can see that for these two problems, we are better than mixed integer programming. And this is just to wrap up. So we have shown that with our model we can handle 400 units, which is a realistic size for the unit commitment problem, and the quality of the solution is not worse. Is not too far from the solution from mixed integer programming, and these are just future directions that we can take. So, for example, we can relax the constraint of the symmetry that we are considering. We can add storage, and obviously one of the main things to consider is stochastic commitment problem.
So on one of your earlier slides, you mentioned risk, and I'm guessing that by this you mean risk that demand exceeds supply, or that supply exceeds grid capacity. Is that correct?
Yes, I mean, once we have, there are different kind of risks that we can consider. This is in the optic that with the more penetration of stochastic resources, basically, if there is a static drop in the wind production, for example, the power system cannot be ready to react to this change. So we need to put additional capacity to the power system in order to prevent the risk of this sudden drop or something like that.
So it doesn't look like there's any explicit model of this risk.
Sorry?
It doesn't look like you have any explicit model of this risk of change in your formulation of the problem. Are you handling that by essentially placing buffers on trying to have enough extra demand or enough extra supply to handle possible changes in demand?
At the moment, we are not taking into consideration the risk problem. One thing, and the way it's handled now is that we have a reserve on the total capacity that we can produce. But this is not enough if we increase the stochastic resources.
Any other question? I'm going to have to do all the work again. I mean, so related to what David was talking about now, the market operators for managing this process. sometimes what they, well often actually, what they do is they do an analysis of what would happen if one of the generators was going to be available for some reason. So I was just wondering whether that would be, I don't know, practical to do some of that. What kind of planning techniques do you think, for this N-1 reliability analysis?
Yes, so at the moment, this reserve constraint that we have takes into account this eventuality of failure. But I mean, we have these can be restricted constraints in the future when we are considering stochastic generator. And at the moment, it is working. In the future, we don't know. And yeah, it's a matter of
So I think it did come through in your talk, but I just wanted to emphasise that this piece of work was about us trying to race a MIP, basically. We wanted to see how well can planning do by comparison with MIP solving on the same problem. And we're pretty pleased with the fact we got so close. And what wasn't on the slide, but we spent quite a lot of time looking at, is the fact that the actual solutions generated by the panel were very, very similar to the ones generated by the MIP. So not just in terms of time to solve the problem, but in terms of, in fact, you did talk about the quality aspect. So that was the goal of this paper, and all these other extensions of future work.
No, that's very nice. We will dominate.
Yeah, we'll dominate.
All right, this is the end of the session.